So I want you guys to think about one more thing, okay? So here, notice as I bring this closer, if it's over here, this leaf isn't up very high. As it gets closer, it's much more pronounced, right? So there's some relationship with the distance and the force that this thing feels, all right? So let's talk about some actual math, because we've done no real math yet. And as you know, there is no real physics without real math, okay? So let's talk about forces acting over a distance. Now, what is a force that we already know about that acts over a distance? Gravity, right? All the other forces we talked about in physics
201.
required some sort of contact. Normal force, you have to be in contact. Friction, you have to be in contact. Tension, you have to be in contact, okay? The only one that can magically act on you, even if you're not touching it, is gravity, okay? So the only forces that do that are the 4 fundamental forces, all right? Let me remember the 4 fundamental forces. Yeah, gravity, electromagnetic, which I'm guessing is the one we're going to talk about in this class, and then the strong and weak nuclear force, which we don't talk about too much until you go to 210 a little bit, and then grad school. Okay, so you're not required to go to physics grad school, so don't worry about those. Okay, so forces that don't require contact. The one we're familiar with, gravity. Okay, this is the Earth. This is the moon. We have forces that look like this. Okay, they're an action-reaction pair, equal and opposite forces, but they don't have to be in contact. Okay, and what did the force of gravity, what's Newton's gravitational law? What did that look like? What's the force of gravity?
Capital G.
Capital G. And then, if you want to make it a vector, right? So here's the Earth, and here's the this is R. It goes from center to center, right? So this is M1, M2, and you can switch this, right? They'll just change the sign, but it points R hat is the unit vector that points along R. Okay, so this is a force acting over a distance. This is Newton's law of gravitation. Okay, neat. What's special about this constant? It's constant. It's called a universal constant, which means it works everywhere in the universe. Okay, remember little g is pretty much stuck with Earth, right? And it changes depending on where you are. But big G is always the same everywhere. So we have this universal constant. What do you need in order to have gravity act on you? Mass, right? Mass. And remember, gravity is pretty weak because we all have a fair amount of mass, right? Do you feel attracted to the person next to you, gravitationally?
Okay, this is that contact.
Emotionally, that's different. Your emotional mass is a little bit different. But you do feel attracted to the Earth. Why? Huge mass. So in order to actually feel gravitationally attracted, you need a lot of mass. But you've noticed here, just a few differences in electrons can create force with an electromagnetic force.
Isn't it also because of the fact that the Earth is closer to us than the others, and the others would end up having a weaker gravitational pull than the Earth?
What others? Like from Lost? Oh, the other planets are really far away. So there's mass, and then there's inverse squared distance, right? So this falls off really fast because it's squared, and it's in the denominator. Okay? All right. So this was always an attractive force. Okay? Does gravity ever shoot you off the planet? No, it's never a repulsive force, which is good. That would be awkward. But remember, we just said that you can have attraction and repulsion from charge, right? Opposite charges attract, like charges repel. When you stick the balloon to the wall, that's an attractive force, but when you put all this static in your hair or when you put all the static on the peanuts, they repel. Okay, so it has two versions, and that's because, can mass be positive or negative?
No.
No, but charge can be. So when we write out Coulomb's law, oh wait, here, attractive and repulsive, all right? So force due to electric charges is called electric force, just like force due to mass is called gravitational force. And it turns out Coulomb's law looks a lot like Newton's law for gravitation. We have some constant, let's call it K for now, all right? And then we have Q1, Q2 over R squared. And once again, this points towards the other charge. So if we have a charge here, let's call that Q1. Charge here, let's call that Q2. We connect them, this is R. The forces once again can either point in, like this, if one is positive and one is negative, or out, if they're both positive or both negative. So when this gives you a positive, either because both of these are positive or both of them are negative, that's a repulsive force. When this gives you a negative, because one's positive and one's negative, or one's positive and one's negative, that's an attractive force. Okay, so it even includes in the math whether it's attractive or repulsive. Yes?
So in like those bullshit James Bond movies, we're like, oh, we make the Earth or the balloon crash into the Earth. And then like, they use like a magnet or something. How do they throw off the force of like the repulsion?
But let me just I'll get back to that question. I'm not even sure how to answer that question. So in a fake movie, how does the physics work?
Yeah, it's like, yes. Like, is it possible to actually?
No. Yes-ish. We could talk about this later, because I only have 1 minute to introduce this. So I put these in absolute values, so we don't have to worry about the signs yet. But this force looks like this, and we call this K. But it turns out this is our universal constant, okay? 4 pi times some constant. Of course, 4 pi is also a constant. But epsilon naught is something called the permittivity of free space, okay? And that sort of has to do with, so free space, what do you think that means? It's a vacuum, yeah. So this is the permittivity, whatever that means, in a vacuum, okay? So permittivity kind of means how well the electric field works in a vacuum, okay? And it has this number that's really easy to remember, 8.85 times 10 to the negative 12. Cool. You might want to write that down. And then usually we can also say it as K, which is just this whole thing. We can call that K. And that's actually much easier to remember. It's 9 times 10 to the 9th Newton meters squared over Coulomb squared. And I just want you to see, this number is fucking huge. Okay? Does anybody remember what big G was? Oh, that sounds fun. You guys are all like suffering.
6.67.
I think it's 10 to the negative 11. 10 to the negative 11. Okay? Is that anywhere near as big as this? No, 10 to the negative 11 is really small, which is why you don't feel attracted to the mass next to you, okay? But you would feel attracted to them if they were charged, okay? So, or repulsed, you know, give or take. Which equation? This is just 1 over 4 pi epsilon naught. So this is an epsilon. It's like a weird Greek squiggly E.
What's that?
K. K is the electrostatic constant, so that's 8.99 times 10 to the 9th Newton meters squared over Coulomb squared. Yes? Yeah, that should be a little K. Also a constant K, all right? Mainly the thing you want to remember is the number. For Coulomb's law, this whole thing is K, and it's 9 times 10 to the 9th, okay? Newton meter squared over Coulomb squared. And you're going to say, well, I'm never going to frickin' remember Newton's meter squared over Coulomb squared, but you can find it from here, because what is this going to have to be in? Newtons, okay? So this is going to give you what? Coulomb squared. This is Coulomb's, this is Coulomb's. Coulomb squared in the numerator and meter squared in the denominator, okay? That means you have to cancel meter squared, you have a meter squared on top. You have to cancel Coulomb squared, you have a Coulomb squared on the bottom, and you have to have newtons left over. Okay, so that's how we end up with Newton meter squared over Coulomb squared. All right, so we're going to use this constant a lot. If you can't remember it, make sure you at least write it down. Okay, yeah. And of course, we have the permittivity of free space. Anybody remember what free space means? You want to guess what free space means? Yes.
Three-dimensional area.
That is sort of space. Why is it free space? What's it free
it
of?
It can be any value.
Vacuum.
Vacuum. It is free of molecules, okay? Free space means vacuum. And this is going to come in later, right? Because this works in a vacuum. Are we in a vacuum? Take a deep breath. Does that feel like a vacuum? No. So if you can breathe, you're not in a vacuum, okay? If you're in a vacuum, you're not answering the question. You're dead. So free space means vacuum. And of course, this situation, it's pretty close to free space. So even if you're in air, it's pretty close, okay? But there's lots of cases where you can have charges that are not in free space, and then this changes, okay? And this is going to be really important when we talk about capacitance, all right? Because has anybody heard of a dielectric? Two of you. Great. Well, you'll all have heard of it soon. But there's other materials you can put between charges, and it changes the force that the charges feel, okay? Just like, swimming in air and swimming in water feel different, okay? Charges respond differently in different materials too. So here's our force. This is a constant. Charges determine how strong the force is, okay? And it's also inverse squared, just like gravity, so it drops off pretty quickly, all right? If you're right next to a charge, you're going to feel a pretty strong force if you also have a charge. If it's way over there, you don't care, okay? So inverse squared means it drops off pretty precipitously, all right? Okay. All right, so we're going to try an example.
Okay, so we're going to try this out, just sort of testing out our Coulomb's law force equation. We're going to start, we have 2 nanocoulomb charges. They're 4 centimeters apart on the x-axis. The x-axis is kind of not a big deal here, but we're going to deal with it anyway. So let's start with the x-axis. Okay. There's our x-axis. Okay, so we have 2 10 nanocoulomb charges. So let's put one here, and we'll put one here. Okay, so we'll call this Q1 and Q2. This is going to be equal to 10 nanocoulombs. This is equal to 10 nanocoulombs. And then right smack dab in the middle of these, it's not quite the middle, we have a 1 nanocoulomb charge. We'll call that Q3. That's 1 nanocoulomb. Now the distances between these things, we see this is 4 centimeters, and then we also see from here to here. Draw that better. We have 4 centimeters from here to here, and then we have 2 centimeters and 2 centimeters. So then we have to remember what we do with force, because remember our force equation in this case is force, sort of force 1 on 2 or whatever. Let's call this force AB just to not be confusing. Is going to be K, QA, QB divided by R, which is the distance between A and B squared, and that's going to be in the R direction. So this Coulomb's law, and this is our Coulomb force. Okay, so this is a vector, but remember how forces work. Remember, these things are repelling. So let's start with Q1, right? Q1 is going to have a force, because remember, we only care about this guy right here, right? So we only care about this charge, the forces on this charge. Obviously, this charge also has a force on this charge that goes that way, but that doesn't really matter. So for our purposes, we want to deal with the force of 1 on 3. Okay, so we can write that out, and the force of 1 on 3 is going to be K, Q1, Q3 over our 1 to 3, which is this, right? This is our distance, r1, 3 squared. All right, this is the scalar, and we know that the direction is going to be to the right because we drew it right here. Okay. Also, if you want to look at the force here, the force from this charge, Q2, on Q1 is F2 on 3. Sorry, on Q3. So the force from this charge on this charge is going to be F2 on 3. And so we can write that over here. We'll say F2 on 3 is K, Q2, Q3 over the distance between R2 and 3, which is still 2 centimeters squared. And we know that that's going to point to the left. Okay, so if we want to solve these, first off, we can notice that as we plug in the numbers, these are constant, right? So they're going to be the same. This and this, these are both 10 nanocoulombs, so they're going to be the same. And then Q3 is the same, it's 1 nanocoulomb. And then these are both a distance of 2 centimeters, which in this case is just the way the problem's written. That's not always going to be the case. And remember, when we're doing these things, in this case, we only care about the forces on this thing. I mean, there's obviously a force this way on this thing because they're repelling each other, and then there's forces from this guy on this guy, and there's forces from this guy on this guy. There's a lot of forces going on, but we're only being asked about the 1 nanocoulomb charge between them. So we only calculate the forces on the 1 nanocoulomb charge. And we know these forces are going to be equal, and we know they're pointed in the opposite direction. They're not an action-reaction pair, right? But they're equal and opposite in this case because of the way we're set up. So remember, this one is going to be to the right, which is plus x hat, and this one is to the left, which is minus x hat. So when we add these up, we know we're going to get 0, but let's go through the process just to be clear about how it works. So this is going to be K, which is 9 times 10 to the 9th Newton meters squared over Coulomb squared. You also need to convert your Q's to coulombs so that they cancel. So this will be 10 times 10 to the negative 9 coulombs, 1 times 10 to the negative 9 coulombs. All of this divided by, it has to be in meters, so convert from centimeters to 0.02 meters, and that is squared. Don't forget to square that, okay? And you can look at your units. That means coulombs and coulombs cancel with coulomb squared. And we get meters squared canceling with meters squared because there's this square over here. And so we're going to end up with something in newtons, which is good because this is a force. So when you plug all this in, you get 2.25 times 10 to the negative 4 newtons. Okay? And that, if you want this to be a vector, the way that you rewrite that is 2.25 times 10 to negative 4 newtons in the positive x hat direction. And now you have a vector. You can do the same thing over here, but you can see all of the numbers should be the same. So we're just going to copy this and move it over here. And once again, same. So we move that over here. okay? But the difference here is F2 on 3 as a vector is going to be 2.25 times 10 to the negative 4 newtons in the negative x hat direction, right? So that's going to be pointed to the left, okay? So when you add up the net forces, which is something we call superposition, that means F net as a vector is F1 on 3 plus F2 on 3 as a vector. So that gives us 2.25 times 10 to the negative 4 newtons minus 2.25 times 10 to the negative 4 newtons, which is 0, okay, 0 newtons. That's our answer. And we're going to make that right there. And that's in the x direction, but it doesn't matter because it's 0. Remember, this is x hat and this is x hat. We left that out. But since we moved to the negative over here, so that's where the negative from there goes. Just as a reminder, this is our answer for our charge to the left, and this is our answer from the charge to the right. But because we're worried about the charge in the middle, that means we just have to add up all of the forces, and there are 2 forces. Okay, so this is a problem I want you to try to do on your own before you watch what I'm doing, because I want you to practice what we did. So we're walking through basically the same thing as the example, but now we've changed the configuration slightly. So we still have these 10 nanocoulomb charges. They're still 4 centimeters apart, so we're going to draw out our x-axis. So here's our x-axis. Oops, that's a plus. All right, we still have our 2 10 nanocoulomb charges, right? And so we'll still call these Q1 equals 10 nanocoulombs and Q2 equals 10 nanocoulombs. But now, instead of one, and they're still 4 centimeters apart, so we can draw that too. Let's see. So that's still 4 centimeters total. But now we're putting this other charge in a different space. So it's 1 centimeter from one and 3 centimeters from the other. So let's put it over here. And we'll call this Q3. It's equal to 1 nanocoulomb. So when we draw our distances, okay, here, this one is now 1 centimeter, and this one is now 3 centimeters, okay? So once again, we're going to figure out the force on our guy in the middle. So this is the one we care about. We're only calculating forces on the guy in the middle. So remember, each charge is going to have 2 forces on it, one from each of the other charges. But because we're asked for the net charge on this guy, we only calculate the net charge on that guy. So we'll start out with calculating this force. And look, you'll see, we know because there's an inverse thing happening with Coulomb's law, these 2 forces are pretty close together. So you can assume that the force from this charge should be pretty big, okay? Similarly, this charge is far away, so that force is going to be relatively small, okay? So remember, we're once again calling this, this is F1 on 3 because this is charge 1 and this is charge 3. Okay, so it's the force of this big 10 nanocoulomb charge that's close over here. And then over here, we have F2 on 3. So once again, we're going to use Coulomb's force law. So that's F is equal to K, Q, let's call it QA, QB over R. This is the distance between QA and QB, AB squared. And that's in the R hat direction. This is a vector. And this is your Coulomb force. Okay, so we're going to write this out. We're going to start with the force of 1 on 3. Remember, we know the direction is to the right, and that's going to be positive x hat. So we'll write this as a scalar, and then we'll deal with the vector part later. So that's going to be k q1 q3 over r between 1 and 3, right? So that's going to be our 1 centimeter one. That's our r. Squared. Very important to square that. Okay. We can also write out over here f 2 on 3 is k q2 q3 over r 2 3 squared. Okay, and remember this is to the left, so that's going to be negative x hat if you want to make that a vector, and this is going to be to the right, so that's positive x hat if you want to make that a vector. Okay, plugging in actual values, this gives us 9 times 10 to the 9th Newton meters squared over Coulomb squared. That's our K. That's 1 over 4 pi epsilon naught. We have 10 times 10 to the negative 9 coulombs. We have 1 times 10 to the negative 9 coulombs. And all of that is over 0.01 meters quantity squared. So when you plug all that good stuff in, you end up with something that looks like 9 times 10 to the negative 4 newtons. Remember, this is plus x hat, and so this is plus x hat. Okay, so that's our answer for that one. And we'll write that out like this. Okay, we can do the same thing over here. The only thing that's really different over in this one is that we still get 9 times 10 to the 9th Newton meter squared over Coulomb squared. 10 times 10 to the negative 9th coulombs, 1 times 10 to the negative 9th coulombs. But we know down here, now our distance for this one is 3 centimeters. So we write 0.03 meters and we square it. And that's going to give us a very different answer over here. That's going to give us 1 times 10 to the negative 4th newtons. And that's going to be in the negative x hat direction. So we have 2 different answers because the distances have changed. Okay, and just like before, we want our F net, right? So the net force on this 1 nanocoulomb charge to be F1 on 3 plus F2 on 3, remembering all of these are vectors. So essentially we have 9 times 10 to the negative 4th newtons x hat, and then that's plus 1 times 10 to the negative 4th newtons negative x hat, so we can move the minus. We get 1 times 10 to the negative 4th newtons x hat. Remember, the x hats are important because we're adding vectors. You can't add vectors unless they're along the same axis like this, otherwise you have to do all kinds of trigonometry. So this is going to give us not 0 anymore, because you can see this force is much bigger than this force. It's going to give us 8 times 10 to the negative 4 newtons, and that's going to be in the x hat direction, which is to the right, which is a very different answer from 0. And now we have this value. So we guessed that this wouldn't be 0 because now the forces are not canceling out, they're not equal, and we were correct. So that means we have a pretty big force, bigger than our last one, even from one of them, because when you have these, because of this square, right, when you have these charges close together, you get big numbers. When you have the charges far apart, you get smaller numbers. Remember, electrostatic force is a force, and therefore it is a vector. So if you have this situation, what's the force? So let's say this is the force, the charge we're worried about. Okay, let's see, these are fixed and maybe this one can move. All right.
So what's the force here from this charge? Which way does it point?
Down.
Down. What about the force from this charge?
To the right.
Points to the right. Where's the net force? This way. Okay? And so remember, anytime you're asked for a force with a bunch of charges, when you're looking at these charge distribution problems, you have to make sure you're adding your forces as vectors. Let's say this is 2 newtons and this is 3 newtons. Is the answer ever going to be 5? No. Okay, don't just add them up. Make sure you draw the picture, you know which way your vectors point, and you add things up as vectors. If you have an x and y, now you're in a trig situation.
Okay, so we're really just doing the same thing we were doing before, but now we have more charges in a two-dimensional configuration. So we have to deal with both x and y. And because these are vectors, that makes a difference in how we calculate things. So to start out with, we want to identify the forces that we're dealing with. So we're looking for the charge on Q2. And Q2, let me just sort of circle it. Q2 is this guy, okay? So because we're looking for the charge on Q2, that means we need to figure out the charge of Q1 on Q2. And because these are both negative charges, that's going to be a repulsive force. All right, and then we also need to figure out the charge of Q3 on Q2. And because that's a positive and negative charge, that's going to be an attractive force. So it's going to point towards Q3. So we're going to call this F3 on 2, and we'll call this one F1 on 2. Okay. So looking at this configuration, we just need to write out these forces, and we're going to use Coulomb's law like we did before, but we're keeping in mind that these are vectors, okay? So I'm going to get rid of this color, and we're just going to look at these two forces. We're going to start with F1 on 2. And that's, of course, K Q1, Q2 over R squared. We're sort of ignoring this direction. We're just finding the magnitude in this case, and then we'll add in the direction later. So when you plug in those values, remember K is 9 times 10 to the 9th Newton meters squared over Coulomb squared. Okay, and then we have our different charges. So we have Q1, which is 4 times 10 to the negative 9, because this is nanocoulombs. So that's in coulombs. And then we have 1 times 10 to the negative 6, because that's 1 microcoulomb. Notice we're ignoring the signs in this case because we already know the direction. We've already calculated out what that looks like. And then you're going to divide this by the distance between these two things here. That's our R in this case. And that's going to be 2 centimeters, so 2 times 10 to the negative 2 meters, and that's a total quantity squared. Okay, when you put all this together, this gives you negative 0.09 newtons, and then if you want to go back and make this a vector, then we have to look at it as down. So remember, we can call this I and J, or X and Y. So if this is X and Y, this is going to be in the negative Y hat direction. Or you can call this, so Y hat or J hat, there's a negative that goes from this pointing down. Okay, so we can acknowledge the negative sign. You could also write this as sort of, negative Y hat, because then here you have the magnitude, here you have the direction, and then when you simplify it, you could move the negative out here, but you can write it however you want, as long as you recognize that you have the magnitude of 0.09 newtons and it's going to be pointing down. Okay, for the other charge, we have F3 on 2, and that's going to be similar. We have K Q3 Q2 over r squared, where this is the distance between 2 and 3. Up here, that r was the different distance between 1 and 2. Okay, so when you plug these things in, you still get 9 times 10 to the 9th Newton meters squared over Coulomb squared. Oops. And that's just our constant K. Then you have 8 times 10 to the negative 9 coulombs. That's charge 3, Q3. You have 1 times 10 to the negative 6 coulombs. That is charge 2. And then you have the distance between these things, which is 3 centimeters. So 3 times 10 to the negative 2 meters. And this is a quantity squared. Okay, so that's this distance. And you plug all those things in, you get 0.08 newtons, and that's going to be pointing to the right, so that's in the x hat, positive x hat direction. All right, so we're going to call that a vector. So now we have our 2 vectors, and we want to add these vectors up. So we want our F, our total force, total is going to be this force, oops, plus this force. Okay, which is the same as saying this is equal to 0.09 in the y direction. So negative 0.09 y hat plus 0.08 x hat. All of this is in units of newtons. But remember, you can't just add these things up because they're not pointing in the same direction. We know our resultant vector is going to look something like this, okay? And because of that, what we really want to do is take these vectors and sort of, oops. So we want to sort of figure out what that's going to look like. So the resultant vector is going to look something like this, and this is going to be our F2. But in order to get this, we kind of need to do some trig, and you're really just calculating F2. So in order to do this, we need the magnitude of this, so F2, and we also need the angle, this one, okay? So to get the magnitude, that's pretty easy. F2, so this is a vector F2. The way this works is you just do Pythagorean theorem. So this is going to be the square root of 0.09 newtons, and there's a negative there, squared, plus 0.08 newtons squared. You plug these things in, and that's going to give you a magnitude of 0.12 newtons. That is our magnitude of F on 2. But we still need, oh my gosh, we still need a direction. So for our direction, we need to figure out theta. So we use tan inverse of y over x. So remember, y is going to be 0.09 newtons over 0.08 newtons. And so that's going to give us an angle of 48.4, and we could call that degrees south of east. And now we have both a magnitude and a direction. So our total force, F2, is going to be 0.2 newtons, 48 degrees south of east. That's how we're going to describe the whole thing. And now we finally have our answer, because remember, if we're asking for a force, and a force is a vector, we need both the magnitude and the direction.
Quietly answer this to yourself, and hopefully you weren't looking at the screen 5 minutes ago. Let's discuss. We'll vote again. Convince people.
That 66% has
They're not a lot
concentrated
more.
on the other door.
Okay, so let's write this up. Okay, so here's A. So we'll call this QA, QB. And remember, our R is just the distance between the centers, so that's R. Okay? So, force of A on B. Well, that's going to be K, QA, QB over R squared. Everybody agree? Okay. F of B on A is K, QB, QA over R squared. Are these things different?
No.
No. Okay. What would we call this in terms of physics 190?
Oh, that's the third law.
Third law, right? This is an action-reaction pair. The force of this on this should be equal and opposite to the force of this on this, but we're just asking about the magnitude, okay? This is not a vector, so the magnitude should be the same. The signs will be different, but the magnitudes are the same. Everybody okay with that? Cool. One thing I noticed from listening to the video that I recorded is I say okay way too much.